Thank you. Right. Welcome everyone to this is number 4. Wow. Welcome to the 4th lecture in advanced computer architecture. I'm going to ask all of you, please, if you can close your laptop, please. Unless you are really in the stock market and every second really matters. Remember, we have a camera in the back. Last time I was snitching over some of the screens. There were some YouTube, some cartoon show. Okay. Yeah. All right. So we'll continue with the memory hierarchy. Last time we discussed the cache, right? The cache design is really important. We are going to take attendance by the end of the lecture, not now. And we'll continue now with the cache. Hopefully with the next week, we'll start with the DRAM device, which is a very important topic. A lot of research on the cache design, how we improve a lot of things on the cache side, as well as how we improve the computation or accessing the memory over the DRAM device. Okay, hopefully you remember this picture from last lecture. We discussed that the easiest way to move data into the cache from the DRAM to the cache is through direct map. Direct map means we read some of few bits of the LSB in the address of the memory, and based on those bits, we can map one cache block into certain dedicated location in the cache. Every time we move something with these exact same LSB bits from the memory, it will be assigned always to the exact same location in the cache. Okay, and this is very important. However, we said this is very trivial, and normally this is not the thing that we use in real processors, or at least the modern CPUs. Okay, and we discuss something we call n sets or n-way set associative cache, which means we divide the cache into sets. In this example, for example, we have 4 sets, right? And in each set, we have about 2 ways, okay? 2 ways to choose one of these locations to assign a cache block into these, in one of these sets. And we still use the exact same thing as in here, the LSB bits, to choose which one of those sets to have a cache block in it, okay? However, when we get a conflict, meaning that we want to assign one cache block from the memory to the cache, let's assume the LSB is assigning to 0, right? So we want to assign that cache block into that set. Then we have 2 possible ways. Either we push the block in here or in there. In there, we have only one possible location, so we always are going to have a conflict, which is a cache miss, okay? Or a conflict, meaning that we need to evict the cache block that exists in the cache, remove it back to the DRAM, or just ignore it, and then replace it with the new one to the same location. So once we increase the number of ways in each set, we're going to reduce the miss rate or the conflict rate, okay? We could have normally a multiple of 2 or to the power of 2 as number of ways or number of sets. However, that is not a requirement. It's not really, we have to have it as 2 ways or 4 ways, 8 ways, 16 ways, and so on. We could have 3 ways, 4 ways, 5 ways, 6 ways. However, we are going to ignore some of the hardware that we are going to use. For example, we use muxes to assign one of the cache blocks to each of those sets. And that mux normally is multiple of 2, right? Or at least power of 2. So we could use 3 input pins of the mux, and the rest will be ignored or not utilized. So that's the drawback of using that or of doing so. When we have the entire cache as one set, we call it as fully associated. Fully associated, meaning that the cache block is free to be allocated in any way within the cache size. And you can see the limitation once we have the cache block assigned to anywhere, basically mean more complex hardware because we need to decode more bits and we need to check more location in order to be able to know where that cache block exists, right? Otherwise, we cannot fetch it. Over here, we already know that it cannot be in any of those. It should be only in one of them based on the LSB bits. So it's easy to go to that set and fetch the corresponding block, and that's it. Over there, we have to check really most of these based on the index and the tag bits, and then we can know where's the data.
Is it like nice software or addresses like that, or?
So it's a mix of hardware and software because there are a decoder, there are a muxer, and there are a comparator to compare with the tag that we stored. You remember last time we said we store the index, which is the LSB. We have the index. The index is basically the LSB bits, exactly the LSB. However, the address of the block is really large. Even if we consider the 4 LSB bits from the address, we still have remaining bits, right? And whenever we have a block in the cache, we cannot know whether that is something coming from the block that we are looking for, or just by coincidence, the LSB is shared between both of them. That's why we need to store that as a tag. We call it tag, okay? And this is the index. So we still store the index and the tag in order to be sure that the exact address we fetch from the DRAM is the one stored in the cache, okay? So the software will decide on the policy on where to place that block and how to replace it. Okay? But the hardware also needs to adapt to that. So in order to be able to compare to the entire set of bits, like the entire length of the address, we need a comparator that can accommodate that width, right? Also, in order to be able to fetch one of the block from the entire cache, we need a mux over there, right? So we can serialize all the data that we got from the block into the data path, okay? We will see now a few examples of the policy, or basically the software, how we decide on which block to fetch from the memory and how to decide on which block to be replaced. It's not just fetching, but also want to bring more blocks from the memory to the cache, and we have the cache is full, right? How to replace some of these cache blocks with certain block that we are moving. All right. So in this plot, we have in the x-axis the L2 cache size, and the y-axis we have the hit rate. The hit rate. What does it mean, the hit rate? You remember from the last lecture? Number of accesses. We said the rate, right? So it should be divided over something. No, not the number of instruction. That should be the hit rate per instruction, right? But this one, the hit rate without anything, meaning over the number of memory accesses. How many times we send requests to get data, right? How many of them miss? How many of them hit? Okay, if we consider the miss, mean a miss rate. So we divide. So we have a lot of requests. This is a cache. Last lecture, I start considering the notes I'm drawing here. So hopefully it's clear. I think so. Yeah. Is it? Yeah. So this is the cache. This is the memory. How many times do I send requests? Or basically, this could be the CPU. Which part in the CPU is sending the request to the memory? You remember? We already discussed it. Which part in the CPU is sending the request to the memory? Something we call MC, the memory controller. The memory controller. We will discuss a lot of details about it next week. Okay. The memory controller is inside the CPU. It's something responsible for sending all the requests to get more data from the memory. Okay. And now, how many requests do I send through the memory controller? Let's say 10 requests. How many of them already exist in the cache, and I don't have to go back to the DRAM and fetch data? Welcome back. You got your visa? Congratulations. All right. How many of them miss? For example, 5 times I have to go to the memory and get data. That is 1/2 miss rate. Okay. Likewise with the hit rate, which is the complementary. All right. This is again the cache size, right? And this is the hit rate. When the cache size was very small, we expect the hit rate to be small, right? And the miss rate to be much higher. Why is that? We have a lot of data to be accommodated in the cache, but the cache is small. I cannot have everything set in the cache. So I have to gradually bring data over time to the cache, process it, evict it, or remove it, replace it, bring new data to the cache, process, and keep moving, right? This is how I work with the small caches. That's why I expect the miss rate to be very high, which is about 55% or so. Once I increase the cache, what I would expect, increasing the hit rate, meaning that I really don't have to go long trips. Everything exists next to me. I'm the CPU. I'm having everything from L1 cache, right? Everything as a hit. However, there is a certain cap. There's a certain threshold that I can reach with the hit rate. Why is that? Regardless, whatever I increase the memory size, I cannot achieve 100% of hit rate. That is something very important to consider, which is the access pattern. The access pattern. So where is my data? How large my data that's needed for the program, right? And what is the access pattern? Is my data, all of it, set next to each other in the DRAM so I can easily fetch all of them and I can know the spatial locality and the temporal locality of those data, right? So from program to program, it really depends. Some of them will benefit from larger caches. Some of them will never benefit, especially if I'm working on data that's small. It's already can fit fully in the cache. If so, increasing the size of the cache will never benefit me. You'll pay more money because remember, caches are very expensive. If you increase the size, you will pay more money. Your device or hardware component will be really expensive, and it will not see any benefit in terms of performance. Two, complementary to each other, right? So more misses mean I'll get less hit because all of them are related to the memory request. Memory request is the same, 10. How many of them miss? 2. Then the remaining were hit. It cannot be either this or that, right? It cannot be something else. It's either hit or miss, right? So they complement each other to 100%. All right. So now we understand the story with larger or smaller cache, right? But there's something important with it, which is the associativity. Okay. Why it's important? It's related to the conflict, the number of misses. Okay, yeah, I have large cache. Now I can fit more data. However, I cannot fit it anywhere. I'm limited within a number of sets. Do you remember the previous picture? I have the whole cache empty for me. However, I'm only required to fit that cache in that set, for example, number 1. And that set is full. Then it will be a miss, although the cache is empty, right? So that is something very important to pay attention to. Now, with increasing the associativity, it means I have more ways to fit the cache block in one location. So even if that set is nearly full, right? If I increase the number of ways, for example, 4 ways, and this is full, so I still have 2 more. If this is full, and I have more ways to fill within, remember, this is single set. This is single set. However, I have many ways. The more ways I increase, it means the more possibility or probability to reduce the conflict, okay? Because I still have more spaces to fill with the same cache block. So the moment I start increasing, you can see over any of those columns, for example, over here, you can see by increasing the number of ways, I'm increasing the hit rate. And this makes sense, right? Because I will never have a conflict. I always have more spaces to add cache blocks to the same set. It doesn't matter what other sets are, whether they were empty, they were full, I don't care. I'm just focusing on single set in the cache, okay? Excellent. This is something advanced. Maybe I have, I think, half slide on that. So we can. Yeah. Maybe we'll touch upon that toward the end. I have, I think, half slide on that. There are a lot of research topics just in this. Imagine just on the policy, how to increase the size, how to evaluate it, how to find the optimal way where to place first and then replace, and then increasing priority of a cache block in the cache. We will see over time. All right, so hopefully all of you agree that more ways mean more hit rate, because I always have more to add, and I will find that cache block in the cache, meaning I don't have to go back to the DRAM and bring it. Every time I can bring more caches and place it in the cache, which is very handy for the CPU. Large cache size sometimes will benefit me, sometimes not. So it's not necessarily to benefit me all the time. Even if you increase it by 32 meg, you remember the 32 megabyte example we discussed last time about Tesla cars? Excellent. So that was single level of cache, and it was a huge, really huge. Okay, we don't have L1 or L2, or basically that cache is L1. Okay.
And can you please go back to that? Now, my intuition from the graphics, we go to associative, they're all same.
Not really. You can see the difference is really slight. Yeah, we still have like very minimal difference over there between, for example, one, which is direct mapped, right? Direct map and the other. So when we talk about n ways, probably there's minimal difference, very minimal. Maybe we don't see it over here. And maybe there is no difference. It really depends on how many cache block we assign to the set and the access pattern, okay? So it depends if those cache blocks that we access always from the DRAM will be over one set or distributed over the entire set. However, what we really need from this figure is that when we increase the number of ways, it means more complex design, because we need a bigger comparator to compare to those ways and a bigger mux and decoder, right? That's the cost that we are paying to increase that number of ways. However, it's improving the hit rate. By how much it improves, we have to evaluate it based on each application separately, because each application accesses the memories really separately. Each application has what we call a memory pattern. And that pattern is really important, how many times we access the memory. Is it memory intensive, like AI and games, for example? All games are memory intensive. All the time we are fetching some data from the memory. Every move we do with the cameras, any move you do, it causes more data to be rendered. That's why you get continuous graphics as if you are in real city, for example, or real home. That's meaning I'm accessing the memory all the time, bringing more data to redraw the scene for me, right? That is what we call a memory-intensive application. So we talk about hardware complexity because I need all the time to compare with more tags and more index or indices, right, to access the right data on each of those locations. And we talk about a mux to get back the cache block to the mux and move it to the data path. So that means more time, more energy, right? More time and more energy. Let's see. Here we have the cache size in the x-axis. Here we have the time. Here we have the energy. And here we have the associativity. Remember, when we talk about one way, what does it mean? One way means each set has only one way to place a cache block. We don't have alternative. It means a direct map. A direct map. So only we rely on the index to place a cache block in one single location. So it's very easy for us to access that cache block because we are sure that the cache block will exist in that particular location, right? That's why it's very simple design. The complexity is much less than what we have in n ways. Now, by increasing the n ways, we increase slightly the time, right? The complexity of the hardware and also the energy because we have more component now, more complex design. Of course, when we have the entire cache, as accessible, that is the most time-consuming design and the most complex design, which means there is no sets. There are no sets at all. The entire cache is just one set, and I can place that cache block anywhere. It means the hardware is really complex. It needs to compare to the entire cache to know where I'm placing the cache block, especially if I'm using something called random replacement policy, meaning that I randomly pick one cache block to be evicted and then place the new one. Okay, this is something really stupid because next time I'm going to read the cache block, I don't know where is it. Now think about 32 megabyte cache size, right? And I have to really go through the entire thing. Good luck finding it. I already moved it. Okay, so the relative access times and energy consumption increase as cache size and associativity are increased. Hopefully, you're already convinced by that. Slower cache access time and more expensive hardware. We talk about comparator, tags, and mux, and I have a picture to show you the exact hardware in the next few slides. So what are the issue in set associative cache? Why we're talking a lot about the n-way associativity? If you remember last lecture, I told you that this is the norm for all modern CPUs. So any modern CPU should use n-way associativity, not the direct map, not the full associativity. And I gave you assignment last time. How many of you solved it? You have to check your CPU, right? You have to go to the cache and get all the specs, all the specification to know the size, how many caches, how many level of caches, what kind of associativity used there, and so on, right? How many of you check all those details? 1, 2, 3. Okay. Yeah, please try your best to understand that. It's really important to move forward to know these specification in modern CPU, especially if you have i9 or i7 processor. Okay. Also for AMD, it might be very interesting to know that. All right. So there are issues that really depend on the size or number of ways per set. So we talk about one way, it's not good because we always have conflict, always have one location. 2 ways, try to solve that problem, but gradually, minimally. If we increase it to 4 ways, 8 ways, the more, the better. However, now we have the question of what we call a priority, right? Which block has more priority than other to keep it over something else? Because whatever the number of ways we have, there is a probability that we will have a conflict, right? Even if we have a lot of ways and that set is becoming full of cache blocks, now which one of them is more important than the other? And there are a lot of things to think about that. So indicating how important it is to keep the block in the cache. And remember, the cache is something close to the CPU, meaning that whenever the CPU needs more data to be processed, it should be in the cache. That's why we really worry about which cache block to keep, which cache block to be removed. The key issue here, how you determine or adjust block priorities. There are three key decisions in a set: insertion, promotion, and evacuation. Insertion, when it's empty, right? I want to insert a cache block in a set and it's empty. Where to place it? You can go in order, right? First one, place it. If it's full, move to second. If full, keep moving, right? You could do it randomly. You could use some of those bits, for example, in the tag and the index to decide where to place it in the set. In the promotion, if I'm looking, some of the policies, for example, require least recently used, most recently used, something like that, which really require the cache block to be accessed already soon or in the near future or in the near past in order to access that again or to keep it or to replace it, right? Based on that, I couldn't change that priority for some of the cache block in order to keep it in the cache. So hopefully you understand how the insertion, promotion, and evacuation happening in the cache, at least in general idea. Now we are going to jump in the details of each of those items and see what are the available algorithms to do that. Okay, so we have insertion, promotion, and evacuation. This is the architecture I promised to show you. Here what we have as a cache. This is what we call as a cache line or a cache block. Okay, this is important. So whenever we talk about cache block, what does it mean? It means a lot of data. When we say the size of the cache, for example, 32 megabyte, what does it mean? It means only the data, which is starting with the words over here. We don't consider the tag, we don't consider the index, we don't consider the other bits that needs for housekeeping. There are a lot of bits needed beside the tag and the index. The index and the tag are important to fetch back the cache block. So we use them, we use a comparator, as you can see over here, to compare what we have in the tag and the index. Once we get a hit, it means that is the address that we were looking for. That's why we need a comparator. However, there are other things that we should consider before we get back the data. For example, this is only the address, but there are some other bits to indicate, for example, whether the cache block being modified before or not. Remember that cache block, we bring it from the memory, and we could do a lot of computation on it at the CPU side. And now we have updated result. Do we need to store it back in the DRAM or keep it in the cache, because probably we are going to use it later on very soon? If we push it back to the DRAM, we will pay a lot of cost for the mess penalty, because now we need to go again through all the hierarchy of the caches, all back to the DRAM, and then bring it back to the CPU. So this is very important metric. That's why we keep some of the bits. For example, the D means dirty bit, dirty bit. Dirty means that the block being modified. Okay, so at the CPU side, we do a lot of computation. We change some of the result in the cache block, and we keep it in the cache. That's why we keep that bit, which is very important. The V is valid, whether that cache block is valid or no longer needed. Okay, even if we update it, becomes dirty, right? And we update it, but we don't need it. We don't need to store it back in the DRAM, back to the storage, right? So we just keep it, and we make it as invalid. Means that is a very good candidate to be evacuated. Okay. And again, one important thing, whenever we talk about the cache size, it only means the words, the data, the actual data we bring from the DRAM. It does not cover anything related to the tag, the index, the validity, and the dirty bits. Okay, although those sometimes minimal, like very small number of bits, so we are talking about kilobytes. Sometimes in meg, it really depends on how large your cache and how many of those are stored and what's the width, the bit width of this information. Okay. All right. What else? Yeah, in this example, we are talking about 512 byte cache. Okay, so we're storing this much of data, and we have 32 byte blocks contain 16 cache blocks. So yeah, so that was an example, not necessarily to be this number. We have a lot of examples by the end of the lecture to see a lot of those architecture, how they are different between GPUs, CPUs, and even between different processors like i9, i7. We saw one of them in the Tesla, the cache. Okay, now let's talk about the evacuation, the replacement policy. Which block in the set to replace on a cache miss? Any invalid block first. For example, if something I don't need and it has invalid bit in the cache, do you remember the previous picture? So that is a first candidate to be replaced, right? If all are valid, then I cannot replace randomly. Or there is a policy called random, so I can do that, but that should be with good reason. Otherwise, I will always have a miss rate. Always, I'm replacing good ones. The first one is random, right? That's the easiest choice, easy to implement. I really don't need sophisticated hardware to do so. However, there are more nicer designs. For example, FIFO. What is FIFO? First input, first output. Why is that? First input means I used it earlier, right? Something I already used in the past. There is less probability that I'm going to use it later on, right? I might use nearby blocks, which is spatial locality that we discussed last time, right? So any block we access, probably we are going to access the nearby blocks, right? The least recently used, what does it mean? Least was not used within the last, I don't know, a number of cycles, for example, right? Now, what's the difference between FIFO and least recently used? FIFO does not consider when it was used. I don't care when it was used. It cares only when I insert it in the cache. I could insert it just 1 minute ago, right? And it was the first to be inserted. I could insert it 10 years ago. Maybe not. The PC probably already flushed all the cache, right? But maybe 1 minute ago, 5 minutes ago, and so on. However, the least recently used, it's not about when I insert it in the cache, right? It's about when I use it. So that is the important difference between them. Not most recently used. What does it mean? Oldest, yeah, or older, not necessarily oldest. Older covers already those, right? Least recently used, but also cover something between least and most. Like it was not the most frequently used or recently used. It was not the oldest. It was somewhere between. Older, right? Least frequently used, I access that block many times. But why would someone do that? Why would someone replace a block that we frequently access? Sounds terrible, right? That's the idea, the whole idea behind the cache. Again, as a reminder, please keep all laptops closed. Least frequently used means it was not frequently used. So this makes a lot of sense, right? Rather than most frequently used to be replaced. Every policy I'm choosing, there's always a price that you are going to pay. For example, the FIFO, you have to track which one, or the order basically, not only which one. It's the order of every block. Which one was first, second, third, and that's required maybe a counter or maybe more bits to be stored in the cache line, right? For example, how many lines in the cache you have, and based on that, how many bits I need to fit that number, right?
Is there like a blanket policy?
Excellent. That's a very good question. So we have something called optimal replacement policy, but that optimal in one aspect, which is someone could say, my device, whatever I'm designing for Tesla, for NASA, for Microsoft, for Google, for OpenAI, my policy is to get the lowest miss rate. That's what I care about. I don't care about the price. Whoever buying a Tesla could afford $10,000 for self-driving, extra feature, right? Then I care only about performance, how to reduce the miss rate, so that I always decide very quickly on self-driving whether I should turn, avoid an accident, and so on. In this case, I would evaluate all of these and find the one that's optimal for miss rate. Someone could argue, no, I need a portable device, a very small one, and I care really about the number of components that I'm going to include. Because the more component, the more hardware, I'm going to increase the size of my device. That's my requirement. For example, I can use it as earbud, right? Or something as very smart in my eyeglasses. In this case, I would look for someone with the smallest hardware requirement, okay? And that is the question, or which one is optimal? Two. No, not consuming, it's replacement. Yes. No, this is always data. That's why whenever we mention this is the cache size, then this is how much data we could fit. Because data always will dominate. Whatever we store next to it as number of bits, including the tag and index, will be minimal compared to the data. The data is a lot, right? A lot of words. Could be like 500 kilo, for example.
No matter what the policy, everything is still going to be stored in.
For example, random. I don't store anything. I just make random choice.
Okay.
Then I don't add anything to the cache. But most of these, yes, would require to add more bits to the cache. You remember the previous architecture we discussed, this one? Probably you would need something in here, right? This is how I would know that this was least recently used.
So kind of like trade-off. Whichever policy you take, the still concentration of the impact.
Definitely. That's why I told you there's no optimal in everything. It should be in one aspect. So there's always trade-off. Want to go with more complexity, then it might be really optimal in terms of something, right? And I think Naeem did a great job. I saw his email yesterday. He clustered the research paper that we assigned in the list, right? So I don't know how accurate that cluster. So probably you verify. But based on his clustering, he said there were about 8 or 7 papers on caching. So probably you'll see some of these topics, especially a replacement policy. And that's a very important metric. Okay? Blame him, please, if that grouping was not accurate. Okay. Yeah, I was going to do that, but then I said, okay, let them at least scan in most of those papers. And then we will cluster them, as I promised, when we fix the schedule. When we fix the schedule, it makes more sense that we have 2 topics in the same day on the same topic. So both of them on caching, for example, both of them in processing and memory, and so on. That will make more sense. But for you, you really don't care about the grouping. I would believe you would scan all of them first, at least from title, and then you'll see something might be relevant to your research, or something that, okay, I know nothing about this. Let's take the challenge and challenge myself. Go ahead with that, with something that I really don't know. Believe me, all of them are hot topics. All of them really needed. Whatever the amount you spend in effort in these will benefit you in interviews and more knowledge, in thinking in different ways about the computer architecture and so on. How many of you already submit their preferences? Excellent. Okay, about 70, 60% maybe. So we have about, I think, 2 days. I'm sorry I cannot extend it more. I have really to move forward and decide on the first group, the first victims on presenting in the first week. Okay. Yeah, there's something nice, since we already answered the guild question about which one is optimal. There is no single best solution, so it makes sense to use hybrid replacement policy. For example, on L1 cache, I could use one policy. In other caches, I could use other policies. Depends on the size, how many miss rate I would have. If the miss rate is really minimal, then I would go with something very simple, because I don't expect to have a lot of misses over the flow. Okay. And that's very important to understand what we discussed in the beginning of the lecture, which is the memory pattern. This is extremely important. Hopefully we'll have one lecture on how we can check the memory pattern of an application. You run one application, whatever it is, and then you monitor the request that application issue, or the CPU issuing to the memory. How many times I would access the memory, and how I could redesign my general purpose computer to reduce the number of misses. For example, sometimes it's really easy just to replace the cache. Some of the caches are inside the CPU. So it's not like DRAM. You just unblock and you put more advanced DRAM over there. You need really to change the whole CPU for that. Which one is optimal? We already discussed it many times, but we will see some examples now. I have also an exam question already included the slides, so you can see what kind of question or how you deal with these topics, for example. So the first one, which is least recently used, and I think the name is explaining itself, right? So evac the least recently addressed block. So you go over the set. If it is full, which one was accessed recently, less recently, until I decide which one was least recently accessed, and then I just replace it with a new block. That's it. Okay, that's in case we have a miss rate, or a miss, basically. So the problem, I need to keep track of access order of the blocks. So we already discussed how to solve it just by adding more bits to the address over here. For example, you can have 0, which is as not the most recently used, for example, right? And then less until I define which one was least. Now, in two-way set associative, you can, if there is a set and we have 2 ways, what does it mean? I have either here or there to be replaced, right? Either this or that. What does that mean? It means the number of bits needed to define how recently was used is single bit, either 0 or 1. 0 means, for example, was not recently used, or this one was recently used. That's it. So single bit of overflow, right, or overhead to add to the cache size. Now, when we increase it to 4 ways, what will happen? 2 bits, right? Makes sense. It's very easy. Remember, all these bits will not be included in the cache size as a number, as specs and specification. Oh yeah, I forgot I have chocolate. Yeah, let me start. Or I forgot. So 0, 0, 0, 1, 1, 0, 1, 1, right? As simple as that. Then I can define what is least recently used. Is it 1, 1? Is it 0, 0? It's up to me. Based on that, I can use some kind of comparator and fix it to 0, 0. If this is 0, 0, replace that. Done. Okay? Of course, the more ways, more complex it gets. It's not about number of bits only. Now we talk about comparator. Now maybe something else, and so on. It depends on really and replacement policy, how complex we could go. Okay, there's bits and logic, which is the comparator, and repeat for n-way. If we talk about 16-way, how many of you find out that their cache, at least L1 or L3 cache, were 16-way associative cache? 8 ways? Cannot be more than that. Cannot be less. Most of the laptops, 8 or 16 ways. How many of you 8? How many of you 16? Most of you none? 0 ways? Direct map? Probably direct map from 20 years ago. Yeah, please check it. It's really important as a computer scientist or computer architect to know these details. Okay? No. It's hardware, right? You need comparator, bits, and so on. That's always directly go to the microarchitecture of those caches, right? What you can configure is something else. I think in 2 slides we'll talk about bypassing the caches. Bypassing the caches. Sometimes you don't really need to bring cache block from DRAM to L3 to L2 to L1. You can directly skip and go to L1. And this is very frequent in GPU design. When you do program in GPU, you'll see some instructions allow you to fetch data from the DRAM or from the global memory all the way to Scratchpad, okay, to do computation directly on that. So sometimes you can control something in the cache. Approximation of least recently used. As we said, least recently used does not scale well. So every time I increase the number of ways, I need to increase all the hardware, number of bits, and so on. So that's why most modern processor, if they implement LRU, and probably most Intel, at least i7, you will see something around LRU, which is a modified version of the least recently used, not the original one. That's why we talk here about approximation. So don't implement the true least recently used, because again, scalability is very bad, right? And we need a lot of hardware more. So sometimes the original one, the one we discussed in the previous slide, we call it true or perfect least recently used. Yeah, we talk about the complexity. Some example on the not or non-perfect LRU could be not MRU, most recently used. That's a variation of the LRU. So if you see those terms, you probably understand now what's happening with the cache. The hierarchical LRU, instead of considering all the whole space as one candidate to be replaced, you could go with half of it on something, the other half on something else. In this case, you can reduce the number of bits. Okay, so you can define it as subgroups. One group on doing something, the other group on doing something else, right? And then you target one of those group within the set to be always a candidate for replacement. In this way, for example, I have 4 ways in one set. I consider one region to be candidate for replacement. This way, I need only 1 bit, either 0 or 1. Although it's 4 ways in one set, but I subdivide the set into more groups, and then I mark one of the groups to be candidates for replacement. Vectum, next vectum replacement, that's another variation, which means one of the level of the caches will be a vectum, the other level will not be a vectum. And then when we ever have a block in the vectum, then we move it to the next vectum or next cache level, basically. So you don't replace it, you push it to the next level, you move more cache blocks, okay? What is the optimal? There is an algorithm that claimed to be an optimal called Biladi OPT, optimal or optimal replacement policy. And in this one, we replace the block whose next use by the algorithm is the furthest in the future. The furthest in the future. What does it mean? When we look at least recently used, we look in the past based on used, right? We use it already in the past. Now we look in the future. So we have to check the next instruction, not only the previous instruction. And that is really something hard to predict because those instruction in the next were not fetched at all. We didn't fetch them in the CPU, so we don't know what's happening next, right? So this is kind of challenging how you would predict which block is going to be used or referenced in the future. And not only in the future, but to be furthest in the future, not in the near future. We'll see an example on it and how it works. So this is the paper if you're interested in it. And this is optimal in what sense? We discussed that we cannot have one optimal solution. It should be in one aspect. What could be? Sorry? One way? No. What is the metric, the performance metric that we are considering this paper to be optimal? Miss rate. Excellent. So miss rate. Chocolate? Yeah. So miss rate, this paper is optimal in that. There are other papers that try to combine other metrics. So if you're interested, probably you have it. You have this paper, I think, in the paper list. This paper from Georgia Tech on replacement policy that's optimal in more than miss rate. And they did thorough analysis also to the optimality of that algorithm. Okay? Yeah. So there is one very important thing to be considered here, which we call a miss overlapping. A miss overlapping. What does it mean? A miss overlapping. Do you remember we discussed that when I draw this shape and I said this is the CPU and we have 4 cores? Do you remember this example? I think it was the previous lecture. We said in i7, a single core issued 2 references per cycle per core, right? In i9, how many reference? 5. 3 for read, 2 for write, right? That's single core, single cycle. So imagine this is i7. Now a single core would send 2 requests to the memory. Give me data, 2 cache blocks, because 2 requests, right? And this is per cycle. Now, if the memory or the memory controller or the caches are available, right, and the latency is very minimal, then they would supply my demand very quickly in parallel. So if I send 2 requests and both of them were misses, then the cache would bring those 2 cache blocks directly and quickly as if it is single request. So the miss penalty I'm going to pay as if it is single miss penalty. Okay, because they were in parallel, and the cache were able to supply the cache blocks in parallel as well. And then if the miss penalty 10 nanosecond, do you remember those numbers from the pipeline? We said for a DRAM, the miss penalty is, don't read. Excellent. 50 to 100 nanosecond to get a cache block from the DRAM. But this is only for the DRAM to L3 cache. Now, if we want to bring it to L2, we pay more penalties, right? Bring it to L1, more penalties, until we move to the register file in the CPU, right? So imagine this is 10 nano, and this is 10 nano. If both requests were supplied in parallel, then what I'm paying is only single 10 nanosecond. That's why I said here, a miss overlapping. So this is raising the question that aren't all messes equally the same? Like whenever we have a miss, just go to the cache, pitch that cache block, insert some penalty, and that's it. If I have 10 requests, then I pay 10 times that penalty. And no, it's not as simple as that. Some of the misses is what we call isolated. Isolated. It means it's not overlapped with anything. All the cores, for example, busy in doing computation, they are not sending requests to the memory. They are not asking for more cache blocks. Only one core could be asking for single cache block. In this way, this is what we call isolated miss. And then I'm going to pay 10 nanoseconds. If I have 10 isolated requests, like in sequential order, then I'm going to pay 100 nanoseconds. Okay? And this is what the paper is trying to rely on. That's why I'm focusing on the isolated one. Try to have them in sequence. Whenever there is something that I might need in the future, but it's very far from me, then I don't need it currently. It's just evicted and bring more cache blocks to that. Okay? Hopefully everything was clear, because we'll have an example on those policies. At least replace, least recently used, and the Biletti optimal policy. Okay? Same between and it depends. In some processor, they optimize the read and write buffer. So you can place a block on the buffer, and then you can bring the whole data in one request. Some of them, you have to pay more penalty to bring more cache blocks. So we will see probably next week the architecture of DRAM, and then you will understand what is on the data path to bring data from the DRAM to the caches. And then you will see exactly what's happening over there. Okay? But at least what's important to us is the time, which is actually the thing we rely on when we calculate the miss penalty or the performance of a program based on the instructions. All right, so now we talk already about replacement. We talk about insertion, which when the cache is empty, where we're to insert those blocks. Now let's talk about, we already perform something on the cache block. We already compute it, and we make it dirty, meaning updated. We update that cache block. Now what? What should we do? We have an updated cache block in the cache. Should we send it back to the DRAM, store it there, and hopefully we will store it again in the SSD? So even if we turn off the PC, we're not going to lose this data. Or should we keep it in the cache in a sense that we will need it soon, very soon? So for that, we have two ways. Okay? The problem with not doing anything, if we don't do anything and we keep it in the cache, in the same place, we have a real problem about the inconsistencies. The data that we have in the cache, because we made it dirty, remember, it's dirty, meaning that it's updated, but the copy in the DRAM was not updated, because the CPU has no access to the DRAM. Every data we update in the CPU would be either in the register file, which is internally in the CPU, or in the L1 cache, or L2 cache, or L3 cache. Okay? Especially if the D bit is 1. It means that block was dirty, okay? Was updated. In this case, you have the L1, L2, and the L3, and the block that we update is here. Now there are different designs for the processor. Some of the processor, when we bring data from the DRAM, we bring it to L3 cache, right? And then we move it to L2, we move it to L1. Once it's in L1, we already have a copy of it in L2, in L3, and also in the DRAM. Okay? Some of the designs, no. Once we bring it to L3, we move the whole block to L2. It's no longer in L3. And then we move it to L1. It's no longer in L2 and L3. So if it is dirty in here, we just have to push it back to the DRAM. Okay? If we don't do so, and there are multiple copies in each of those caches, then we will have that problem, which is inconsistent data. This one is updated. This one was not updated, was not updated. What's in DRAM and storage was not updated. To solve that, there are two ways, either write through or write back. And you can guess probably what is happening from the name. In write through, we immediately update lower levels of the hierarchy. Whenever we update a cache block, we directly update everything. Write back, we only update lower level of the hierarchy when an updated block is replaced. When we are going to replace that block, so meaning that we are going to lose it, then we are going to store it back in the lower level of the hierarchy. Both strategies use write buffer to make writes asynchronous, of course. Yes, because I don't want to get the CPU stalled. For example, just waiting for that block to be written back. So I do it in a synchronous way because I don't care now. Because I already have it. If there is a memory request to that block, I already have it in the cache. So I don't have to worry about the other copies in the other level of caches. This is an example on write-through. This is a very famous question in the exams. Luckily, you don't have exam. Maybe you can consider one. So this is the cache. This is the main memory. I have certain location over here. Remember the index, which is the LSB bits. So it's very important to consider the LSB first, and then the rest of the address, which is the tag. So here, where's the LSB? Is always the things to the right side. That's why we call it least significant. It means even if I change those bits, the value wouldn't change much. Do you remember the binary conversion? 1, 2, 4, 8, 16, 32, and so on, right? If I ask you convert 10 in decimal to binary, what you would do? 10 is 8 and 2, and the rest will be 0. So that's the binary. If I ask you about 16, 16, the rest 0, right? Now, if I change anything to the right side, I'm going to change a value of 1 or value of 2. But if I change from left side, I'm going to change 32, 128, 64, and so on. So the value of change is really big in the most significant bit. So that's why I consider only the LSB from the memory address in the DRAM to assign or to know where's the cache block or the cache line. And then after that, I have the tag, which is the rest of the address. I have it here. Here, valid or invalid. I could have dirty bits. I could have also replacement policy bits, and so on. Too many things I could have. What's important for us is write through is the data itself. Was the data updated? No, right? Still the same. Now, if the data later got changed, in write through, we immediately update the lower level. It means I also have to go back to the DRAM and update that in a synchronous way. Write back, I have the cache, I have the DRAM, the cache sends the data. I already update the data in the cache. Then I have to go to the main memory and update it, but not now, not now. So I keep the old version. You can see the value of the data, which is similar to the old, but here it's updated. So I wait until the replacement policy decide that now it's the time to replace that block, and then I go back to the DRAM and I place the corrected one or the modified one. This way I can keep all the data consistent, so I don't have to worry about the validity of the data itself. Very important question. Which one better? Which one is better? Why? Raise your voice, please. Why? Think about it. What will happen if I frequently change a block? Change, send, change, send, change, send. Come on, I made the caches to help the CPU, but now I'm helping the caches to keep the data. So what will happen? Which one you prefer? Write through? Why not write back?
Write back because that happens when memory is free and there is no transaction.
Okay, someone else? Who said write through? Why? Write through immediately updating the DRAM. Every time I do changes to the cache, go back to the DRAM and update it. So this is probably very nice, very safe, an algorithm, right? Because always all data are consistent. I don't have to worry about whether that block being updated or not, right? Because I always make sure all the copies are exactly the same in content. However, I'm paying something by doing so. What is it? Energy of doing so. Why energy? Why energy? Why time? Then I have to access several levels of caches, right? How about write back? What are the pros and cons? Raise your voice. Penalty of what? Time and energy. Yes, excellent. What else? Inconsistency, because I wait until it gets replaced. So meanwhile, I might need another copy from somewhere else, but that copy being already modified in L1 cache. And remember, what is special in L1? Close to CPU, that's one. What else? Close to what is in specific in the CPU? No, close to something in the CPU. CPU has many of those things, especially modern CPUs, has many cores. Who said cores? Excellent. More, one tar. No, this is healthy chocolate with a lot of nuts. There are a lot of cores in the CPU, and the L1 cache is dedicated to each core. Each core has L1 next to it. Okay, now with this additional piece of information, what are the problem with write back? Remember, write back, you keep it in the L1 cache. Hopefully when it gets replaced, then you move it to other level of hierarchy. What will happen if this has a copy? This is another copy. What did you say? Excellent. You already mentioned it a bit earlier, right? So I have a real problem that each core has its own copy of data, right? Which one to use? Then I have to go back to the DRAM and to check what will happen, or they already propose a solution to it called cache coherence. Cache coherence. This is another very hot topic, a lot of papers on it, on how you make all caches agree on something without paying the cost to keep updating all those blocks at the same time. Cache coherence. Okay. All right, so we discussed a lot of these things. Can combine multiple writes to the same block before evacuation, because write back, I wait, okay? I wait until it gets replaced, and then I push to the DRAM. And this way, I can leverage or exploit that to wait until many of those blocks get dirty, and then I can evac them all in parallel, for example. Then I really don't have to worry about a lot of write back to the DRAM. However, need a bit in the tag store indicating the block was dirty or modified. Okay, we'll discuss that. Write through, much simpler, because every time I update, just push. Every time I update, just push. Meaning that always the cache or the data is consistent. more bandwidth intensive because I'm always busy in sending the data, although it's asynchronous, right? Synchronously getting updated, but I'm still getting the channel to the DRAM much busy with the data. Hopefully, I don't have too much data that was updated because normally I get two variable of data to calculate one variable, right? So hopefully the data I request from the DRAM is much more than what I update as a result. All right, what are the other things that we need besides the data? We talk about valid bit. Hopefully now you understand what is it. We talk about the tag. Remember, what we use to decide on the location is not the tag. It's the index, which is the LSB. The tag is the remaining of that address. Okay, we just consider LSB. How many bits? We don't know based on the design. Could be 2 bits, 4, 16, and so on. And whatever left, we consider it as a tag. Replacement policy, not all of them result in a bit, extra bits in the cache. And we have the dirty bit. Now you already understand what's happening in the dirty, which is something getting updated. I think dirty might not be the right name for the block, right? Dirty sounds like trash, so we don't need it. You can replace it. But in fact, it means updated. I think why they call it dirty, because it will be basically in one L1 cache as updated, and the rest will be not updated. That's why they call it dirty. So they have to handle it in a special way to consider consistent data over all cores. This is the assignment that we discussed last time. However, if we are lazy to check the Apple logo and then go to more info, and then you'll see all the specs of your MacBook, you could go to the website, open it, go to the caches, and you will see a list of all specs for most of the modern CPUs. Okay, and this is a screenshot of that. So you'll see something like that. You'll see L1, L2, L3. If there are L4, L5, what is the processor we discussed last time that has L4? i7. Excellent. What is the model number? You made it up, right? I think I don't fully remember it, but I think it's 4554 HQ. And there are another model from i7 as well that has L4 cache. So you might see also L4 caches. What we can see in the specs, the size, we already know what does it mean. Remember the number we wrote here? It means only the data, okay? Not the other housekeeping stuff. Only the data that we store. Associativity, 8. What does it mean? Come on, we just explained it. You forgot? Go ahead. Yeah. What does it mean? 8 ways in one set. 8 ways in one set. What does it mean? Based on the index and tag, I could target one set where to store that block, and then I have 8 possible ways to place that block. Could place it in first, second, third, and so on. How many sets? 64. What does it mean? We were talking all the time about one set, how many ways inside it. But the cache itself is really huge. Then how many sets we could divide that cache, right? And per set, we have 8 ways. So if I told you one of the ways is this much of size, can you calculate the size of the cache? You multiply number of ways by that one way, and then multiply it by the number of sets. Basically, you get the entire cache size, which is 32 kilobytes. Yeah, this is the way. This is what we discussed. One way is this much of size. So it means this 4 kilobyte. So yeah, this is one way, 4 kilobyte. There's another 4, 4, 4, and so on. How many of them in one set? 8 of them. And then how many sets we have? 64, right? 64. You multiply all these numbers, you will get 32,000 bytes. Okay? The latency, which is the penalty you pay only if you got a miss rate or if you want to fetch data, right? So if you have a miss in here, You want to go to L2 to fetch data from there to L1, and then from L1 to the register file. So now, hopefully, by this lecture and the previous lecture, we already can precisely define all these terms that we can see about any of those caches. In some of them, you'll see a replacement policy. That's a 3P LRU. LRU is the thing we discussed, which is a true or perfect LRU. We told you that most of modern CPUs don't use really LRU, but use a variation of them. Okay. What else? Yeah, I think everything is covered. Please check it. It's really interesting to see, right? All right. At this course about advanced computer architecture, let's go to the advanced stuff. Now we are setting the stage only. What are the directions to improve the caches or the cache hierarchy? When we talk about cache hierarchy, it means any level of cache. Okay. So the first thing, larger block size. But could someone trivially tell you, why not just increase the block size? If it's always about spatial locality, it means if there is a block that I access, probably the nearby blocks might be accessed soon. So if the block size is getting bigger, I'm going to cover all the nearby blocks, right? So it might solve the problem. But it might create other problems, which is instead of one-way size of 4 kilobyte, now I'm increasing it to 16, for example. Then the cache size getting huge. Cache size is huge. What does it mean? Do you remember last time when we add L4 cache, what will happen to the CPU price? Doubled, not just increased, doubled. And when we saw the plot on the performance, did we gain any performance? Only on one particular, or I think 3 points on the graph, right? Those points related to the nearby size. If we reach the maximum size of the cache, we no longer benefit from there. If we are much less than that size, we also will not benefit anything, right? So we pay double, but the performance is not benefiting at all. And not only that, the price is caused by what? Why we pay double? Yes, raise your voice. Cannot hear. Speed, no, not speed. There is no performance benefit, no speed benefit at all. Why we pay double? It reduces misses. No benefit, was no benefit at all. Only in 3 points where we see performance because of the miss rate was reduced. Then the execution time much higher because we don't have to go to other hierarchy or other levels, right? So there is no performance benefit at all. No miss rate, no time, nothing. If we increase that, what will happen with the address? Increase. Excellent, right? To increase the address, what we need to compare the addresses to know that this is the cache block we are looking for. We need a comparator, right? Then we need a decoder. Then we need a mux to fetch the block. So by increasing the block size or the cache size, we are paying more for the hardware because we are increasing the hardware component in the cache. Likewise, when we increase the cache capacity, the exact same story there. I need that side to participate. Please, someone there, save your side. Higher associativity. Why higher associativity might improve the performance? Yes, say again your answer. What you said just a few minutes ago. Reduce miss rate. Excellent. So why associativity would reduce miss rate? Do you remember? Again, this is really important figure. Do you remember one set? We have many ways, right? Too many ways in the set. When we increase the possible location where to place the block, then we reduce the number of conflicts. Okay, it's not always full. So we don't have to replace. So we don't have to apply a replacement policy. Then we don't have to check the replacement policy bits and so on. So we are saving a lot of things by doing just increasing the associativity. And we saw that practically in that figure, if you remember, when we increased from 1 way to 16 way, we saw an increase in the hit rate. What else we could do? Higher number of cache levels. We saw that processor having L4 cache, for example, was not benefiting except in one scenario, which is whenever a memory-intensive application is there. Okay, so it really depends on the user. If he's using that computer for a memory-intensive application like gaming or AI, then yeah, it might benefit. Giving priority to read misses over write misses. What does it mean? We just discussed it just now. When we took how many times do we get variables, how many times we write back the result, right? So reading those variables is more important than writing the result. Why is that? Because writing might not necessarily to be now. We could do it asynchronously later on, which is write back, right? But reading, if we are delayed in reading the variables, what will happen? The CPU stalled, right? Doing nothing, just waiting for data. I fetched the instruction already. I decoded. I know what's happening. I now need the variable, but the variable not in the L1 cache. So I'm waiting for bringing the data. Okay, so that's what we call a stall, right? By doing a stall, how we can address it? If we have a CPU stalled, how we can address? Someone else. Branch prediction, excellent, that's one, which is speculative execution, right? What else? Last topic in computer architecture course, not advanced, but computer organization. What was the last topic in the course for undergrad? Naeem already said it. Who said? Pipelining. What is pipelining? What are you pipelining? Data, not data. What else? What are you pipelining? What is the CPU is processing? Instructions, excellent. So the CPU fetch one instruction in your program, assuming your program has hundreds of lines of code, right? The CPU fetch one by one, right? But now I fetch that instruction, but that instruction needs data. For example, it's doing addition operation. And that addition operation requires two variables to exist in L1 cache and move them to register file in order to be added in the ALU, right? And the result will be in another register, right? But those data are not there. That's why there's stall. So meanwhile, while I'm waiting for the data, I could bring the next instruction and start processing it until I get the data for that instruction, and then I go back and process that. Okay, that's why this is what we call as a pipelining or instruction pipelining. It means while I'm processing one instruction, I could bring more instruction, process them in parallel until I go back, get the data for the first one, and then continue. Of course, as we discussed in the branch prediction, that might result in wasted cycles. Because what if the data that I need to compute in that instruction that I'm currently installed would result in turning over into somewhere else in the program, not necessarily continue with the next instruction. For example, to result in a jump instruction to somewhere else, right? What if I'm pipelining with a lot of instruction and all of them will be wasted? So I might come through that risk. Avoiding address translation in cache indexing, which is something on not touching the address itself, keeping as is. So I already know where to access the exact cache block in the cache. Sometimes I could do compression to the address. Sometimes I could translate it to something else to change the address space. So you could do something with that. However, most of the other things require really redesigning the cache. For example, increasing the size. You don't have control over it. Or increasing the associativity, the n ways. You don't have control over it. So that requires redesigning the system. There are other things that you as a programmer or user of those caches that you can do. And this is a very important topic. We call it a compiler optimization. Whenever we say compiler, it means software, right? A compiler is really a software. When you program in the terminal, for example, you just call GCC. and GCC would compile for you your code, whether it's in C or something, and then convert into assembly all the way to the machine code, right? There are two ways of doing so. There are many other ways as well. One of them called loop interchange. Loop interchange. What does it mean? Shouldn't be in this course, right? So as the name, very smart, the name is telling you loop interchange. It means swapping a loop with another loop. What does it mean? It means we need to have two loops. If there are no two loops, there's nothing to be swapped. Makes sense, right? So that's why we need a nested for loop. A nested for loop. What does it mean, nested? One inside the other, right? As simple as that. Let's see the first one. Here's an example. I think whoever answered that question might deserve 2 chocolate, not 1. There's a for loop, okay? Another for loop. The first for loop iterate over the G's or the J's, and then the other for loop iterate over the I's, okay? And there's a matrix. Apparently, it's 2D matrix, right? 2-dimensional. So I'm accessing rows and columns. And I'm trying to do some kind of mathematical operation. Doesn't matter. Here, multiplication, so just double all numbers, right, of that huge 2D matrix, but could be anything else. Now, in the other piece of code, exactly the same thing over there. I just swapped the 2 for loops. So the I's now become outer, and the J's become inner loop. Which one is better, and why? If you are a PhD student and you are developing a code, you should really pay attention to the very little details in your code, especially if you are developing a C code, not Python. That will really make a huge difference between just this simple swap. The upper one is better. Why? The upper one will iterate 200 times. All of them will iterate same number of iterations, exactly the same. All of them. So all of them will iterate on every single element in the 2D array. Both of them the same in that regard. All of them is the same. Number of iteration is exactly the same. So we have a 2D array, right? This one, we use it a lot. So maybe we can. Please do not open your laptop. Do not use it. This is the 2D. The first one will go this way. We'll pick the first element, then the second, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, and so on. The second one will go 1, 2, 3, 4, 5, 6, 7. All of them will do exactly the same amount of job. Exactly, all of them will iterate over all arrays. The only difference, whether I would go vertically or horizontally. It's exactly the same thing, the same amount of job, same number of instructions, same number of operation. All of them continuous. Why? Why? Which one you said better, first or second? Second. Why? Why it's continuous in the memory address? Let him continue. Why? Be close, very close, yes. Why? Yeah, this is what he said, but why? why the memory addresses are next to each other. But this is also next to each other, right? We are accessing this element, then the next one, then the next, and so on. Remember, which language is this? C. What's special in C? Yes, pointer, yeah, one of them, but not related to this. No allocation, no memory allocation. We already allocate that before the for loop. You deserve to have answer. Yeah, continue. There's more space to answer that. There's one very special thing in C that is row-wise. It's row-wise, or row major data layout. Row major. What does it mean, row major? It means all the data will be stored in the memory as rows. If you have a 2D matrix, it means this entire row will be stored as one block, one cache block. The next row as another cache block, and so on. Or not necessarily each row as a cache block. It depends on the cache size. If it's really fitting like 5 lines together, 5 rows, then all those rows will be consecutive in the cache line. Okay. If we know that in advance, that C language is a row major, then what does it mean? It means if I access this element and then next this element, what will happen? I'm accessing the entire cache block from the memory to the cache just to get one element. And then I flush the entire line. I go to the next row, I bring the other cache line, and calculate just one element in the matrix. So every time I calculate one element here, I'm bringing cache blocks. It depends the number, how many, like it's not necessarily to be equal to the number of rows that as we discussed, but still many of them. However, if we access here, then there, then there, then there, what will happen? We are still in one cache block, and we calculate the entire row. And this will directly impact the performance of our program by just simple swapping 2 lines. Nothing else. We didn't do any optimization, no performance improvement, no open MP, no multi-threading, no SIMD, nothing. What is the difference? This is the blue, this is the red. The red is busy in fetching more cache blocks than doing computation, but the blue one is continuously doing computation as we just bring one cache line and continue with the rest of the line, right? Hopefully this is very important, and you know it as a PhD student, and that's all because the C stores multidimensional array in a row major order. If C did the opposite, then we have to follow that. So it's really not related to the hardware, but much more than whoever designed the language itself. He just made a design choice. I designed C language, for example. I made that row major. I could make it column major as well, and that will do exactly the same benefit that we would expect. Always, that's why we emphasize, you see what was behind the matrix? The memory pattern. The memory pattern is something really important to do when you profile your application. Before touching it, before deciding what to optimize, you have to do what we call a profiling. Profiling is something where you feed your program and you add that tool to profile. The tool will give you the memory pattern and how many misses, how many hits, and so on. And then you can decide what kind of optimization you would do. Some compilers will be smart enough to change that for you, even if you use the red code, like the one in the top. Even if you use it, you might notice the performance is similar to the blue, because the compiler did a great job to optimize your code. And there is a flag that you can add in the GCC, you know, -03, 2, 1, and so on. This is when you run your code in GCC compiler, right? You can add those flags, any of them, and each one of them has a certain level of optimization. 3 is the most aggressive one, so you can go with more optimization, but the performance might not be correct, or the accuracy of your code might not be correct. So you need really to check the correctness of your code after optimization. All right, so we finished the first optimization. That's what you can do in terms of the caching, right? All related to caching. Now another problem, this is matrix multiplication. Matrix multiplication. If you don't know, matrix multiplication is when you have a matrix, another matrix, you multiply the first row with the first column, that will give you the first element in the matrix. Okay, row by column, one element. Then row by next column will give you this element. The next row by first column will give you this element. The next row by second column will give you the last element, and so on. What do you observe in that? We have rows, we have columns, and we have elements. Now, what will happen to row major layout? I cannot do anything about it because I'm accessing rows over here, but I'm accessing columns over there. And I'm accessing elements over there. So one way in doing so is to go with what we call blocking, meaning I divide my data into blocks. So instead of considering all matrix, I cannot go row major, I cannot go column major, I go with the blocks. Means I divide the rows into sub-rows, okay? For example, in here, I take one block, another block, and the result will be in one block, okay? What I have in here, it's not rows, it's not columns, it's a combination of both, right? I have rows and columns, but I don't go with the entire row so that I don't consider one cache block or multiple cache blocks. What I do, I consider partial of the cache block and partial of the other cache block so that I'm between having one cache block and use one element out of it and between using the entire cache block. So I'm going somewhere in the middle, okay? In this way, I'm not ignoring or wasting the entire cache block, and I'm not considering only one element out of the cache block, somewhere in the middle. This way I can do balance between the performance, and that was the second compiler optimization. Please remember those two. This is very important when you write code, blocking and loop interchange. The second thing related to the hardware is what we call hardware prefetching. Okay? Prefetching means how many blocks I'm fetching from the memory. How many blocks I'm fetching from the memory. There are a lot of research on how many blocks I could bring with me from the DRAM, although I ask for only one. The memory controller just requests one block, but I could bring more because the data path from the DRAM to the cache can accommodate more requests. Okay, so let's say if you could have 2 blocks on any mess, right? You could directly increase the performance by a lot, and that a lot is really variable depending on the workload that I'm using. In some workload, it will benefit, especially that in the matrix, for example, I'm accessing the blocks next to each other. So if I access the first block as first row, then probably I need this next row, the third and fourth. So while I'm fetching the first block, I could bring with me more blocks, right? Because I already know that I have a huge 2D matrix that need to be processed. In some workload, I don't see any benefit or very minimal benefit, for example, in here, when it's not really memory intensive and I'm jumping between the location and the DRAM. It's not really sequential access in the pattern that I have in the application. So I'm just fetching one block, and then I jump into very far location, fetching another block, and do the process. In this way, spatial locality will not benefit me at all. There is compiler optimization done with the compiler itself. It might increase the number of prefetched blocks for you. And before, I think we discussed a lot about this. However, there are 2 points. This is multi-level, which is the hierarchy that we've been discussed for the last 2 lectures, right? We discussed many times whether L4 would benefit me, why not going with L5, and so on, right? However, there are 2 definitions that we should pay attention to. Bypassing, which we discussed about the GPU. Some of the GPU will allow you to go from the DRAM directly to some scratch pad or the register file in the CPU. You avoid all the level of caches, right? That's what we call bypassing. Some of them, they do not allow you, which we call non-bypassing caching. Okay. The other one, inclusive. You remember the level of caches? Inclusive meaning whenever I move one block from DRAM to level 3 and then to level 2, it's already contained in the level 3. All the data in here already exists in there. All the data in here already exists in here and also in here. So all of them are inclusive, right? The smaller one already part of the bigger one. In exclusive one, I decide that no, it doesn't make sense. I'm wasting a lot of size, a lot of capacity in the cache, right? So it doesn't make sense to me to make the copies in there. The goal why I need the hierarchy is basically just to bring the data closer to the CPU. So it doesn't make sense to keep the copy in the L2 and L3 as well. So that's why I use exclusive protocol, meaning that if I move the block from one level, I don't keep it anymore there. So I keep it in L2. If I move it to L1, I remove it from L2, keep it in L1 only. Of course, there are pros and cons. That's why we have something hybrid, non-inclusive, meaning that sometimes I keep a copy, sometimes I don't keep a copy. If I don't keep a copy, meaning that if I vect this, right, if I remove it, it's invalid, for example, I don't need it, I don't need to write it back, then the copy in there, I don't have it, then I'm losing it. Meaning that whenever I have a miss, I have to go back to the DRAM, go all the way to the L1 again. But if I keep copies and this one becoming invalid and I replace it with something else, that block I can access again because it already exists in L2. That is the pros and cons between those three protocols. This is another research papers on not considering a block. You can go with the sub block. So instead of moving blocks, replacing a block, updating a block, and evicting that block, now you can consider part of that block to be updated, which a definition we call a sub block. However, everything we discuss as not in data need to be duplicated for every sub block. So now instead of one cache block, we have one tag, one address or index, and one valid, one dirty, and so on. We will have all of those for every sub block within a cache block. Okay. For some application, we might benefit from that. Some other application, there's no benefits at all. Okay. So again, depending on the memory pattern that we would observe, as you can see in the figure below. I want to quickly jump. This we already discussed many times, but please read it. It has a lot of things that are important, especially on the tag and the data itself. The tag and the data. You remember that we have comparators for the tag, right? To check whether that block was valid or not valid. So while we are checking the tag, we could bring the data directly and fetch it with the tag. So we do that in parallel. Instead of comparing the tag and we see if it's valid or not valid, we access the data at the same time and we bring both of them and we access whether it's correct or not correct. In some caches we do that, especially L1 cache. We always do that. The data, the tag and data are usually accessed in parallel because we really need it quickly. And if the block exists in L1 cache, there should be a reason why we bring it to L1 in first place. If it is there, meaning that most likely it will be correct. If the block in the L2, meaning it's a bit far from the CPU, it might not be really needed. So we have to worry about that. We have not to bring the data, and then we realize that the data is not relevant. It's not with the correct address. So why we fetch the data and the tag, and then we do the comparison, and then we find out that the tag was incorrect. Then the data will be wasted. So in L2 and L3, we don't do that in parallel, but in L1, normally we do that in parallel. And with increasing the size of the cache, there is increasing a probability of having that data as irrelevant. So even if we fetch the data and the tag together, it might be just a waste. Okay. Let's skip. I want to show you this use case. I need 5 minutes. How many of you want to continue with the use case? How many of you want to continue in the next lecture? Who says next? Don't be worried. We can make it next. No worries. How many next? How many now? So next is like that. Now is like this. All right. Yeah, next time we can continue with this. I have 30 more slides. The slides we skip over there is really not important, but this is a very important slide, and everything before really important. Next time, I'm going to have the slides on the iCollege. These slides are not there yet, but I will post them before the lecture. Please be prepared for the exam question. Okay, I need a lot of participation. Please try to understand it on your own, and then we will jump directly with answering the question. This kind of question, and then you have a table, and we need to answer it next time, okay? Thank you so much. Enjoy the weekend.